In this lecture, we're going to talk about notches or stress concentrations. The most likely place for cracks to initiate, since we're talking about fatigue, is at a notch or a stress concentration. And it really isn't possible to design a useful engineering structure without some sort of stress concentration of one type or another. Now, if you're taking this class, you're probably already familiar with stress concentrations, but as a quick review, we can give an example of a stress concentration. We were to take a look at a plate with a hole in it in a uniaxial stress field. If that hole was not in the plate, the stress would be uniform throughout the entire plate. If there is the hole in the plate, then we have a localized stress concentration that spikes the value of the stress near the edge of the hole, and it tapers off and eventually becomes equal to the nominal stress or the remote stress. If you've taken a class in theory of elasticity, you've probably gone through the derivation of how the stress concentration factor is defined as the maximum stress divided by the nominal stress for a plate with a hole is about 3. Now this is a very, very large plate with a small hole in it, effectively infinite. You can have finite width effects so that if you have a hole that's fairly large in comparison to the dimensions of the plate, then you can get a different stress concentration factor. And these stress concentration factors are tabulated in various charts. So if you've taken a class in machine design or sometimes in mechanics and materials, you'll see these stress concentration factor charts. Anything that causes stresses to be locally elevated can be considered a stress concentration. It's not just a plate with a hole, but it can be a groove in a shaft, it can be a thread of a bolt, it can be the weld puddle in a welded joint. Anything that disturbs that stress flow can cause locally elevated stresses, and this is the reason why that the fatigue cracks are most likely to initiate in these types of locations. So the KT, that's called the theoretical stress concentration factor, is defined for elastic loading. Of course, when the stress is high locally, it's also easier to exceed the local elastic limit, and you could have yielding in that spot where that stress concentration factor is. Now, the definition of nominal stress varies depending on what the geometry is. In some cases, it's easy to define a nominal stress. So, for example, in the plate with the hole, if it's a finite width plate, the nominal stress is usually defined on the area of the plate minus that of the hole. So it's the thickness of the plate times the net horizontal distance, that minimum there. In other cases, the nominal stress may be defined on other sections. So you always have to look at the stress concentration factor chart in order to determine how that nominal stress is defined. But however it's defined, you should end up, for the same geometry, same maximum stress. Well, in fatigue, there are different ways to approach the effect of notches depending on the fatigue approach that you have, whether you have a stress life approach, a strain life approach, or a fracture mechanics type of approach. And so we'll go through each of these and kind of give you some ideas of ways that you can incorporate stress concentration factor effects. All right, so again, we'll start with a stress life approach, and we'll take a look at the theoretical stress concentration factor KT. Here's another example of a shaft with a circumferential notch in it. Oftentimes, but not always, the nominal stress is defined on the the minimum or the net section area. So it would be whatever axial force there is in the bar divided by pi over 4 d squared. And then the maximum stress would be given by some factor kT times the nominal stress. Now if we were to look at the stress distribution in this bar, I can switch to a different color. On the edge of the notch, it would be elevated, but it would come down here like so. So that value would be the location, sigma maximum. So you often have a non-uniform stress distribution where you have these stress concentrations. Now in the elastic range of the material, the stress concentration factor kT is only dependent on the geometry of the material. I should say only depends on the geometry of the component. Poisson's ratio can affect the stress concentration factor in some cases. For most engineering materials, if you take about 0.3 for the Poisson's ratio, there's not a huge difference. Maybe some materials, metals, about 0.25, 0.33, but right around 0.3, the stress concentration factor will only depend on geometry. So this means you can take the same stress concentration factor, use it for a steel component, or for an aluminum component, or some other type of material, and you still have the same increase in stress locally. If you were to yield the material, then the situation can change. But again, for elastic stress concentration, it's only dependent on the geometry of the component. Another thing I want to point out is that the stress concentration is usually only given in the primary axis. So what I mean by that, we have a kT that's associated with stress in the axial direction, but due to the presence of the notch, you can also generate a hoop stress in this particular configuration. If it's a smooth bar without a notch, you will not generate a hoop stress, but that hoop stress is usually smaller than the axial stress, so it's not of primary interest. But when we get into talking about multi-axial loading, we will be more concerned about what goes on in the other directions. So let me make just a short note about that right here. So I'll say note that there can also be a hoop stress generated in notches with its own stress concentration factor. If you really get into the details of theory of elasticity, you can compute what that is. If you do a finite element analysis of a component, you can determine what that is or approximately what that would be. But in tables, you just don't see that tabulated. Typical ranges for stress concentration factors can be 1.5 to 3.5 or 4. And it's possible to have a little bit higher, but if you get values that are too high, you're going to quickly yield your material after you put any appreciable load on it, and then you won't be in the elastic range anymore. If you want to think of the stress concentration, if you will, of a crack, then that would approach infinity. Of course, at the crack, we talked about how the stress field, the nature of the stress field is a little different. It has a 1 over square root r singularity. So near the tip of the crack, it dies and decays very rapidly, even though it approaches infinity or goes toward infinity right at the tip of that crack. So in general, what you can say is the sharper the notch radius that you have, the higher the stress concentration factor is going to be. If you were to approach a zero notch radius, which would be like the tip of a crack, an infinitely sharp crack, then you're going to have an infinite stress concentration at that spot. Now there are some issues with KT, and I want to bring up a point about maybe more realistic looking structures that you might see maybe in an automobile or an aircraft. All right, so what I have here is a sketch of a control arm for an automobile. If you're not familiar with a control arm, this is part of the vehicle suspension. You may hear the terms wishbone suspension or something like that. And this is kind of a typical component. It rides up and down to kind of help transmit the forces from the road and the vibrations from the road into the structure in a kind of a damped way. So a typical control arm might have some forces acting on it, like I have indicated here, as it moves up and down in the suspension. And so if you look at this, obviously there's going to be some stress concentration in here. There's going to be some places where the stress is going to be higher. Probably, if I were to guess, probably around here, maybe around here, depending on what kind of loading that we have going on. Those would be the places where I would suspect we'd have kind of higher than the highest stresses on that structure. But if we look at those, what do we define as a nominal section in those cases? How do we define a KT for a situation like that? There is no kind of a straight case where we can determine an F over A type situation, or a torsional loading situation with a nominal diameter and a larger diameter, and so forth. And so thinking of it just in terms of KT is sometimes not very useful in some practical situations. Now we're going to talk about finite element post-processing for fatigue a little bit later on in the course. And when we do, please think about this example and how we're going to use the actual elastic stress at that location and not a nominal stress and a stress concentration factor. In the end, they will amount to the same thing, but the approach that we take is going to be a little bit different, kind of numerically. All right, so keep that in mind for a little bit later in our course. So similar to the stress concentration factor, we can talk about something called K sub F, which is the fatigue notch factor. And for this, remember back at the beginning of the semester when we talked about Wooler's original experiments, where he did 4-point bending on train axles. And he looked at some train axles that were of a uniform section. And if we go back and look at his paper, he also did some train axles that had some sort of notch or a groove in them. And so if they were otherwise the same dimensions except with a notch in them, well, what you can do is on an SN curve, the nominal stress time on the log scale with the log number of cycles to failure, you can compare both of these components on the same plot. Now if we think of our SN curve in kind of the longer life region, 10 to the 3, 10 to the 6 or so, again, these are just estimates of when these things would bend over and the endurance limit and so forth. If this is our unnotched bar, if everything else is the same, but we incorporate a stress concentration in it, we will tend to have shorter fatigue lives at the same nominal stress. And so we have an endurance limit for the unnotched bar, and we have an endurance limit for the notched bar. And strictly speaking, the fatigue notch factor, Kf, then, would be the value of the endurance limit of the unnotched bar divided by the endurance limit of the notched bar. And this would be something that would be greater than 1. Now, generally speaking, your fatigue notch factor is going to be a little bit less than your stress concentration factor. So one way that we can take care of fatigue analysis then, if you know your unnotched SN curve, and if you know your fatigue notch factor, well, then you can shift your curve downward by the Kf value, or at the very least, you would shift your endurance limit down by the Kf factor. If you don't know what your Kf is because you don't have the experimental results for that yet, well, you could use the stress concentration factor. Now, I've seen people get into arguments about whether you should use KT or KF in certain situations. From my perspective, it's not really worth arguing about given the scatter in fatigue data. If you're using 1.5 versus 1.4, or even 3 versus 2.7, to me that's not a big enough difference to make a huge impact on the applicability of your fatigue life predictions. There are some other observations we can make about the notched SN curve and the unnotched SN curve. And we can get some more insight as to what goes on at other places besides just the endurance limit based on those observations. So let's list those down and see what else we can say about these SN curves for the notched and unnotched bars. All right, so some observations we can make for fatigue of structures with stress concentrations. One is that the size of the notch makes a difference. So if you have a 1-inch diameter bar, 25 millimeter diameter bar, and you have a notch in it, even if you scale up that bar to 10 inches or 250 millimeters, with all the dimensions the same, the size of the notch is going to make a difference. In theory of elasticity, the stress concentration factor charts, the stress concentration factor is exactly the same as long as all the dimensions are scaled up accordingly. However, if we remember, the fatigue process is a very localized process that involves a certain volume of material that is highly stressed. When you have a very highly stressed volume of material, if it's a larger volume of material in one instance than another, you have more chances for initiating cracks. Although theory of elasticity doesn't have a fundamental length scale involved in it, the material still does. At the very small edge of things, you can have atomic effects, dislocations, grain sizes as we come up the length scale. And all those things are really inherent length sizes inside of that material. And those things will have an effect on the fatigue damage process. The ductility and the strength of the material can make a difference. Strength and ductility are kind of trade-offs. It's a classical trade-off in materials. You can usually have something that's ductile. When you increase its strength, you make it less ductile. Ductile materials tend to be able to sustain high levels of plastic strain easily. Strong materials usually are able to sustain high levels of elastic stress and strain very easily. So you have a trade-off on both edges of your SN curve, if you will. Stress concentration factors don't look at the strength of the material, so that doesn't really factor into it. And the magnitude of loads does make a difference. Even if you don't think you have yielding due to a stress concentration factor, there may be smaller micro features, maybe small cracks, small disturbances in the surface of the material that you're not accounting for in your stress concentration factor calculation that can cause the material to go nonlinear or elastic plastic at that location. So in general, we can say that these observations tend to contradict the theory of elasticity. Keep in mind, theory of elasticity is a certain set of assumptions that we have about a material. They're very good when those assumptions are met. However, theory of elasticity doesn't have any concept of energy dissipation, and the fatigue process itself is fundamentally that of permanent deformation and damage in the material. There's another entire branch of mechanics called damage mechanics, where you can get into some of these minute details and differences at the microstructural level in a material. So we can take a look a little bit more at stress gradient effects. We have a strong material and we have a stress concentration that's kind of a semicircular notch I've shown on the left side. If we have a very strong material, we can have the stress concentration factor times the nominal stress, give us our maximum stress. If that stress level is less than the yield stress, then the stress gradient will tend to look as I have sketched here. If we have a small fatigue crack emanating from the root of this notch, well, it can grow to get to a certain size. And remember, as that certain size increases, then the stress intensity is going to increase and could promote further growth. If we have a material that is less strong, maybe it's more ductile, if we have a stress concentration factor times its nominal stress that exceeds the yield stress of the material, it's going to be a natural limiting of the stress that we can have at the edge of the stress concentration. And so in that case, the crack may only grow a little bit as we get into here. It can't grow any further because it's not propagating due to the drop in stress, and it stays at a relatively short length emanating from that notch. And so your stress intensity may be lower there in this case than the case on the left-hand side where we have a stronger material. So sometimes more ductile is better than stronger. And it also, like I said, depends on the load level. If you're on the right side of the SN curve where you're at near the endurance limit, then probably stronger materials are better. And if you're on the left side, probably more ductile materials are a little bit better. And in most cases, you can't have both things. Now, there is a theoretical relationship between KT and KF. I am going to write it down and we're going to talk about it. We're not going to put a whole lot of stock into this, but we want to see what the form of the equation looks like. You may see this in other fatigue books, or you may see this in software that does fatigue analysis. So there's a couple of these relations that have been developed. Let me write them down and then we'll talk about it. So there's two equations. One was developed by Neuber and the other was developed by Peterson. We're going to talk a lot more about Neuber coming up, but they're both of a similar type of form. One says that the fatigue notch factor Kf is equal to 1 plus Kt minus 1 divided by 1 plus the square root of rho over r. The other says Kf is equal to 1 plus Kt minus 1 divided by 1 plus A over r. And both of these equations, r stands for the notch radius, and A and rho are material parameters. There's been some attempt to relate these material parameters to the grain size near the material. It's kind of a vague relationship, but it's been done. So there are some formulas that kind of relate Kf to Kt. What does it turn out to be? Well, it turns out to be that Kf is a little bit less than Kt. It also incorporates this idea of the notch size through the incorporation of the notch radius, how sharp it is, and then, like I said, these material parameters. I want to show you this equation. We're not going to really use this equation in this class. My emphasis in the class is always to use the data that you have available and try not to rely too heavily on some formulas that really take a good bit of experience and a fair bit of data to help you build confidence in the formulas. Okay, so if you have the data, then use the data. In general, I'd say these are not too useful, and for practical purposes, in most cases, I will claim that you can take Kf to be approximately equal to Kt. Like I said, some people will argue about that kind of approximation. So what can we do to modify an SN curve for situations where we have a notch and maybe we don't have Kf, maybe we do. If we have the unnotched SN curve, then we might approximately have something that looks like this. Put this in a different color. Maybe our notched SN curve would look something like this. We would have an endurance limit then, endurance limit stress for our unnotched material to be about here, and our endurance limit for the notched curve would be, strictly speaking, SE over KF, but we can make an approximation that it's SE over KT. Over on the left-hand side, for the unnotched material, we have whatever the stress level is for about 1,000 cycles. And over here, for the notched, we could take that to be the unnotched S1000 over some KF prime value, which could be determined by a test. So to make this clear, let me write it this way. Stress level for the notched bar at 1,000 cycles would be approximately equal to, or would be equal to, stress level of the unnotched bar divided by some factor that I'm going to call KF prime. You can determine KF prime from a fatigue test and try to extract that at about 1,000 cycles. Well, there's another approach that we can use. You know, if this KF prime is the same thing as KF and KT, well, then this would be a straight shift downward of this entire curve. Usually that's not exactly what we would see in fatigue data of notched and unnotched bars. These are not generally parallel, but there's kind of a slight slope where there's more of an effect on the high cycle region than there is on the low cycle region. So what I'm going to do is I'm going to draw another sketch. But instead of going to 10 to the 3, I'm going to take it all the way to 1 cycle. Out here would be like 10 to the 6 again. Now at 1 cycle, we're at such a low cycle fatigue that we're really very close to the true fracture stress of the material. And whether you have a notch or you don't have a notch, if you're at the true fracture stress of the material, it's only going to last about 1 cycle. So one way to kind of estimate the picture on the top is that if both of the curves, the blue and the red, converge at the same point, then at 1 cycle, then if we were to redraw this so that it's chopped off at 10 to the 3 cycle, we have a little bit of separation here between the red and the blue curve, and there's a little bit of slope that gets more exaggerated as we get down towards the endurance limit. The other points being effectively the same. Here's the endurance limit SE here, and for the notched bar, this would be SE over KF, again approximately equal to SE KT. I'll put on here note scale change. And again, given everything else that goes on and the scatter that we would see fatigue data, well, this isn't a bad approach if you're using the SN approach. If you have an SN approach and it's working well for you, by all means use the SN approach. There are more sophisticated approaches you can use, particularly when we get into strain life, and we would take into account the plasticity that occurs near the notch. So that'll be the subject of the next section here. I think what I'll do is I'll pause this video here and make a separate video for the strain life approach to notch analysis.